Hello, thank you for coming to my talk. Today we'll be talking about using Dart FFI for compute-heavy tasks. There are some other talks about FFI, but we'll focus on slightly different topics. So, starting with what is even FFI, so that we are all on the same page. FFI stands for Foreign Function Interface, and basically it allows us to call other languages from Dart in case of Dart FFI. So we can integrate with native libraries, natively written code, and also Dart FFI allows us to manage natively allocated memory. So we can use the malloc, calloc, free, etc. methods to allocate native memory. And the important part here will be that this memory is shared between both Dart and the native libraries. There are a few cases for using FFI. First of them is integrating with existing native libraries. So for example, SQLite free. In this case, we have a library that is written in some native language, C, C++, Rust, whatever, and we want to just integrate with it in the most efficient way. The second, the only requirement, the library can be written in any language. However, the requirement is that this language exposes the API in a C calling convention. However, that is the case for pretty much every language, and most libraries will be possible to will either do it by default or will be possible to compile in a way that provides such interface. And in the worst case scenario, we may just need to write some kind of wrapper around this library that will expose this API in the required way. The second use case is integrating with the platform APIs. So on the iOS side, all of the API is available in Objective-C, which is superset of C. So we can use Dart FFI to call into those APIs. On the Android side, the C and DK APIs are more limited in compared to Java. However, still there are some APIs that are available in C, and it may be beneficial in some cases to use them. However, with the implementation of JNI-Gen and other FFI adjacent technologies in Flutter, it's becoming less and less useful to use the NDK APIs. And the last use case is implementing high-performance algorithm, and this is the use case that we want to focus on today. So since we're talking about performance, we should first consider other options, because FFI has its own set of drawbacks. So we should first check if we can achieve the same thing in some simpler way. And obviously, when we are talking about performance, first thing that comes to mind is multiple threads. However, threads in Dart, as you may know, are implemented in sort of specific way, because the only access to threads we have is through isolates, and isolates, as the name suggests, are isolated. So we don't have any kind of shared memory. So any data that we want to provide to our worker thread in Dart will have to be copied. And obviously, the problem is that it won't be threads won't be useful for any task that requires large amount of either input or output data. The only case is if the worker thread can load this data on its own, then we don't need to copy it. So for example, if we want to load some data from the memory storage and somehow process it, that solves the issue of copying memory. There is technically a class that sounds like it solves this issue. So we have class in Dart called transferable type data, which states that it allows us to copy data between, or move data technically, between isolates in a constant time. However, while moving the data is in constant time, creating this transferable type data object takes time proportional to the size of the data. So it still requires a lot of time to like make this switch. And what's even worse, it's not like we can create this transferable type data object once and then use it throughout the life cycle of the app. We need to create new instance for each transition between isolates. So we will be creating it over and over again. Also, problem with isolates, the communication is implemented through ports, which are by definition asynchronous. So there is no synchronous communication. Uh, okay. The second option is platform channels, because in the platform-specific code, we do have access to slightly faster languages. So Java Kotlin is slightly faster than Dart, but not by much. But the problem with platform channels is pretty much exactly the same as with threads in Dart. This is actually the same image, just with different descriptions. Again, we don't have any sort of shared memory between our Dart implementation and our platform implementation. Furthermore, there are also additional problems with platform channels because we don't have the same types between the same type systems between Dart and Java or Kotlin or Swift. So we introduce even more problems. And same as with multi-threading, again, the communication is always asynchronous. Yeah. Going forward, FFI. So FFI comes with its own problems. First of all, we are introducing additional language into our code base. So of course, our developers won't be familiar with it at the same level as Dart and Flutter. Also, since we are introducing C in this case, although it may be any other language, we will need to have some level of manual memory management, even if the language on the other side is also automatically managed and garbage collected, for example, Swift or any other high-level language. Still, we will need to manage some memory that is used to move data between Dart and Flutter. On the flip side, we are getting access to low-level high-performance languages through FFI. So, for example, C, which I will be using in this example, but you can also use Rust or any other language. And since we are moving to a different language, we may be getting access to some more sophisticated optimization techniques, such as SIMD, which I will be showing here. Next up, let's look at the difference of performance between languages. So Dart in general is pretty fast. However, by the way, it's over there on the right side. This graph is pretty hard to read since it's two parts and some part of it overlaps. However, here on the right side is Dart, and it's around 5 times smaller than the fastest language. And the fastest language is, no one is surprised, C. Swift and Java are slightly faster than Dart, but still the same order of magnitude. Okay, so I will now show you how to use Dart FFI we'll start in Dart and then Flutter. Methods that are needed to load our dynamic libraries at runtime. We get also method to look up the functions or other pointers from the native site. And we get the native annotation. However, it's still experimental, but I will be showing it as the default solution since it's becoming one. And we are also getting some nice features for managing native resources in the form of native finalizer. I will explain later what exactly native finalizer is. But let's start with native annotation. Basically, native annotation allows us, it's a new API, new annotation that allows us to much more easily create bindings to our native functions. However, keep in mind it's experimental and there are some bugs, some of which I've personally run into, so you need to watch out, and some workarounds will be necessary for now. Also, native annotations, besides simplifying the syntax, has also very nice feature of allowing us to provide or pass type data allocated on Dart heap to the native function. However, I'll go into more details about limitations around that later on. About native finalizer. So native finalizer is a class that allows us to attach some native callback, so native function, to an object in Dart. And this callback will be called when the Dart object is garbage collector. So it's very nice for managing some resources automatically, because whenever the Dart object is no longer accessible, it will be automatically cleaned up on the native side. However, there are some problems with that, because there is a guarantee that this native finalizer will be called and will be called before our isolate shuts down. However, there is no guarantees about when it will be called. So if we have some resource heavy or memory heavy dependencies, we still should be disposing them manually, because Dart may not dispose it promptly. And also there is a additional problem here, and that is that Dart garbage collector doesn't know about the memory we have allocated natively, so it may not be aware that there is a large amount of memory usage on the native side, and won't feel the need to clean up those Dart resources, which are much smaller, but are attached to the large amount of memory on the native side. Next up, we have FFI package. This time this is a package from pub. It's a little confusing because they are named the same. However, this one provides us with predefined functions for allocating native memory, so malloc, calloc, free, etc., and also some convenience methods for converting between Dart strings and native strings, because on the native side, string is just a array of characters with terminator at the end. On the Dart side, it's a different construct, a class. So we need to convert between those two during our communication. Last but not least, some new features that became available on stable in Flutter in the latest Flutter release, and those are hooks, code assets, and specifically for C native toolchain. So hooks allow us to add some additional build steps into the Dart compilation process. So previously, our native code had to be integrated into native Android or iOS build process. Now it can be integrated into Dart. I will show you the difference between those two later. Code assets is the API for defining specifically code being built by, or code built by the hook. And last but not least, the native toolchain is a predefined hook basically for compiling C, C++, Objective-C code. Also, this is the new part in the recent Flutter release. We can create a FFI package which is Dart only, so it's not technically not a plugin. One weird thing here is that it's created with Flutter create, not Dart create, so that's a bit confusing. But besides that, it creates a pure Dart package with just Flutter based example. And This command will create for us the basic framework of basic set structure of a FFI package with the build hook setup and with FFI gen configuration. FFI gen is a package that allows us to generate bindings for our HC code in Dart automatically, so that we have type safe interfaces on the Dart side. I'll go now to the examples. Actually, we can start with creating this FFI package and take a look at the structure. It's big enough. Can make it a bit bigger. Okay, so in the FFI package, as I said, we get the build hook that compiles our code. So this is the configuration of the compilation process. It will be called automatically by Flutter run, Flutter test, by Flutter run and Flutter test commands, and it will compile our C code defined by those source files. We get some default example functions in the source. Here it's a function that adds two numbers together, and there is also some function that takes longer time to show you the asynchronous working with asynchronous functions on the Dart side. And we are getting the FFI gen configuration. So this is the configuration for generating the bindings for our code, and we can take a look at the generated bindings, which look like this. We get those. This is using the @native annotation. So they're defined as external functions and are annotated with this annotation here. Going to our examples of Dart FFI, I show you this. Okay, so first about the function lookup and the @native annotation. So here I'm doing everything manually, so this is written from scratch, it's not generated. And here we are defining our method as external, and we need to provide this @native annotation. And this native annotation also takes a generic type, which is a function time, as you may notice. So we need to do that to provide Dart with information of what the required types are on the native side. So in this case, on the Dart side, we are expecting pointer UTF-8. This is string representation, and int, the standard type, standard Dart type here, length. But on the native side, we are expecting int32. So we need to specify those types in the native type. Similarly, we can define a struct in Dart. So it's just a class that extends struct. The one tricky part here is that we cannot create this class with a default Dart constructor. So we need to either define this factory constructor or just manually call it. So we need to use this special static method struct create provided with the static type, and then we can assign to those fields manually. Here also we need annotations about what this type is on the native side. In this case, it's double, but technically it could be float, right? But we are using double to make it compatible with, to keep the types the same. Also, we can create structs on the native side. So we can define some function that creates a struct and returns it to us. Here we also have a function that takes two coordinates and returns a double, so we can obviously return values from the native side. And also we have function for freeing bitmap. It's just calling free under the hood. However, I want to do some logging so that we can see when exactly this freeing of memory occurred. And we also have an example of a function that sums a list of number. You'll see in a moment why this is important. And we have example of usage of the native finalizer. So actually we can run this Run this example, and then take a look at exactly what the code is doing here. So first, if you want to pass a string to a native method, we need to convert this string from our standard string into the native string, so the array of bytes with a terminator, and get a pointer to it. And this pointer will pass into the method, the reverse method here that expects this kind of pointer. And then on the other side, this method also will return to us the pointer UTF-8. So again, we need to convert this pointer into Dart string with the toDartString method. And of course, since those strings were allocated on native heap, we need to manually free this memory after it's no longer needed. Here we have examples of creation of structs, so we can create struct with this struct create method, and also we can create the second one with this create coordinate function on the native side, and we can calculate the distance. Double is just returned via value, it's copied, so there is no cleanup needed in this case. Next up, we have this this add method. And here is the interesting part of the native annotation, the biggest advantage. Basically, as long as our function is something what's called a leaf function in Dart, so it's A, fairly quick, and B, most importantly, it doesn't call back into Dart. There is no callback to Dart. We can annotate this function as leaf function, and this will allow us to get a pointer to our data allocated on Dart stack. So this uint32 list is allocated on Dart heap, and we are getting the address to it and passing it to the native side. So we can pass large amounts of data without any memory copy in this case. The caveat here is that this method needs to be fast because Dart VM cannot do any memory management during that to ensure that this value doesn't move in memory. So the garbage collector, for example, isn't running while this function executes. However, still we can. It's very powerful that we can pass some data without any memory copy. Alternatively, we still can sort of achieve that by first allocating this data on memory on a native heap, and then getting access to it from Dart. This is exactly what we are doing in this native bitmap class. So we are allocating the data on the native heap. We are attaching the finalizer so that this data is disposed when it's no longer needed, and then we can get access to this data via type data interface in Dart. However, the caveat with native finalizer I mentioned before, here it's currently behaving as expected because we are creating this native bitmap, and we can see print here bitmap created. Then bitmap becomes inaccessible because we've left this code block. We can see that bitmap has been freed. This log is coming from the native side, and then our program finished. So everything looks great. However, if we remove this loop that is stressing the heap in Dart, we'll see that the order has changed. We have created bitmap as expected, but then it became inaccessible, and our program finished. And only after that, the bitmap actually has been freed. So this is what I mentioned before, that native finalizer doesn't give us any guarantees about when exactly this native callback will be called. Okay, moving forward, back to the presentation. Creating FFI plugin, because now I was showing you the FFI package. With FFI plugin, this is the older old way of doing this, we can again create a new plugin this time. Here we need to provide platforms argument as well because it's a plugin, so we have some native dependencies. And here, as we can see, we have Android Android folder, and we have integration with Android build process. So here we have external native build, which will call our CMake, to compile our native sources, which are contained here in the src directory. Similarly, on iOS side, we have a bit of podspec, and also we have this sort of weird file here that includes our shared native code. And the reason for that is that it's explained here somewhere in the comment, is that PubSpec doesn't support relative imports. So we are just importing here or including the native sources in the concrete place within the package. And also similar to FFI package, we get the FFI gen configuration. Oh, there's one more part, and that's important here, and it's the loading of the library. Because since we are not using the at native annotation, we need to manually load our library at runtime. So here we have got this generated code that loads opens the library from a specific path, and then based on that dynamic library object, creates the FFI bindings for us. Here, we can also take a look at the lookup, because since we are opening this library manually, we also need to manually look up those symbols. So in this case, it's generated, and we have this lookup method that is used to find the specific function in Dart. Okay. Going back to the presentation, and the most interesting part of this presentation, the real-world performance. All the examples are coming from my side project, actually, which is a pixel art editor app. So there are a lot of graphics-related algorithms that need to be pixel perfect, and they need to be quite fast, because even though it's pixel art, it may be quite large and it needs to execute quickly. So we'll take a look at two algorithms. First is alpha premultiplication. The second is flat fill, so the paint bucket tool from Paint. About alpha premultiplication, basically there are two ways of storing bitmaps in memory. There is non-premultiplied or premultiplied version, and premultiplication means that RG and B channels are already multiplied by alpha, so multiplied by the opacity. And we are doing this because composition of those bitmaps is simpler and faster. And specifically in Flutter, if we are doing a conversion between bitmap and the UI image class, Flutter expects that this bitmap will be premultiplied. Here is the naive algorithm for the premultiplication. We are just, for each pixel, we are getting the RGB values, we are multiplying it by alpha, dividing by 255 to make it normalize, and writing it back into our memory. And we have the optimized version, which is the same, but it doesn't use any division. It just uses addition, multiplication, and bit shift to achieve exactly the same result. And the results are actually, here is the first interesting part, and a good reminder that during optimization we should also always measure first, because actually, despite what we would expect, the optimized version of the premultiplication algorithm on iPhone is slower than the naive version with the divisions. However, by this optimization on Android, I reduced the time by 41%, and then by switching to C on iOS, we saw reduction of 45%, so almost double the speed, and 63% on Android, so also almost 3 times faster. However, keep in mind that we are comparing here we are comparing against the non-optimized version. So this number compared to the optimized Dart implementation is slightly lower. And on the C side, the optimization of the premultiplication works as expected. The optimized version is faster, and we're reducing the time by 52%, so over 2 times for iOS, and 75%, keep in mind, compared to the non-optimized Dart version on Android. Moving forward to the flat fill. So this is the algorithm for the paint bucket. On the left, we have visualization. On the right, we have example of exactly the image that we'll be filling in. Although keep in mind, those aren't single pixel wide. It's much higher resolution, so this is quite expensive and pretty pessimistic case for flat fill, this squiggly white line that we are filling in. And the results. By just switching from Dart to C, we gained a reduction of 57% on iOS and 40% on Android. And now the question is how fast we can actually make it. So, of course, first option is using multi-threading in both cases, both in Dart and in Flutter. So first, with transferable type data, we actually lost performance. So creating this transferable type data objects was slower than just doing this on a single thread. By the way, we're using 4 threads for all those tests. By using native memory, so this is a trick that technically we can achieve shared memory between Dart isolates using the FFI mechanisms, because we can allocate some data on native heap. It's then manually managed, so we can access it from 2 threads. So with that, we have reduced the time by 59% on iOS and 39% on iOS and 52 on Android. And with multi-threading in C, we are reducing the time by 79% on iOS and 73% on Android. So we have finally got the 5 times speed up that we expected. By the way, we are now comparing against the faster of the Dart implementation. So on iOS, this will be the non-optimized one. On Android, this is the optimized implementation. However, this is not the end, because since we are using C and we have access to all the benefits of the C ecosystem, we can use something what's called SIMD. SIMD stands for single instruction multiple data, and the basic idea is that modern processors can compute the same can do the same computation on many different data inputs, because processors are, for example, 64-bit, right, these times, and for premultiplication we are operating on single bytes, because RG and B channels and alpha are all 8-bit long. We can compute them in parallel, sort of in parallel, on a single thread. So by implementing SIMD, by the way, technically SIMD is partially available in Dart, but it's not really usable at this point. So by using SIMD, we've reduced the time on iOS by 91%, and on Android we've reduced it by 83%. So now we are getting into 10 times speed up on the iOS side. However, as I said, SIMD is single-threaded. I mean, SIMD is using only single thread to compute multiple pixels at a time. So we can combine both SIMD and multi-threading together. And by combining them, with this last implementation using both of those techniques, we are reducing the execution time on iOS by 95% and by 80% on Android. So here we actually lost a bit of performance by introducing multi-threading on Android. So again, a reminder to measure, because the results may be different than expected. We have lost some performance because spinning up those threads is more expensive than the speed up gained by using them. And lastly, I've also tried to implement it in on the GPU, this computation. However, it was only 2 times faster, but I didn't spend that much time on optimizing it. Basically, it seems that copying data between CPU memory in Dart and the GPU was slow enough that it doesn't really make much sense for this specific use case. Because in the end, the computation that we are doing, the promultiplication, is very trivial. So the computational power of the GPU is not really utilized well in this case. So in the end, we've managed to make the iOS implementation over 20 times faster than the Dart implementation, and it's flipped here, and 13 times faster on Android. Okay, that's the end. If you have any questions, feel free to ask them. There are also QR codes for my Twitter/X, the examples on GitHub, and also the editor if you're interested.